A significant atmospheric pattern is currently establishing itself over the United States, prompting operational forecasters at the Storm Prediction Center to use language they reserve for only the most serious of circumstances. It appears the quiet period for severe weather in 2026 has drawn to a close. As these forecasters work, the same reorganization of the Rossby wave driving the impending storms is also responsible for rebuilding a heat dome over the mid-Atlantic, generating dry microbursts in Montana and setting the stage for a 995 millibar surface low to form over Kansas by Sunday afternoon. Amidst this complex atmospheric dance, a G2 geomagnetic storm is also anticipated. Yet, there is a deeper concern that forecasters are hesitant to voice publicly, and it is this underlying reality we must explore. The critical question is not whether this week will bring severe weather, but whether the pattern now locking into place is a precursor to an even more volatile period. If this subject captivates your interest, we invite you to continue this journey with calm space. We value your perspective and would be interested to hear where you are watching from and whether you believe we are witnessing a single, extraordinary week or the dawn of a longer atmospheric shift. At this very moment, the Storm Prediction Center is analyzing a map of the United States that is unlike any other seen this season. The data paints a concerning picture. 17 red flag warnings are active, with 15 additional fire weather watches queued up behind them. A slight risk for severe thunderstorms extends from central Montana down through northern Utah. Layered directly over the fire weather zones is a region flagged for dry thunderstorms. In the crazy mountains of Montana, gusts are forecast to reach 75 miles per hour, while the Blue Mountains of Oregon could see winds of 65 miles per hour. Perhaps most striking are the relative humidity values in the Mojave Desert, which have fallen to just 7%. To put that in perspective, this is a level of aridity drier than the average atmosphere inside a sealed grain silo in mid-August. Every one of these figures, from the warnings to the wind speeds, is being driven by a single, powerful upper-level trough that has just made its way ashore over the Pacific Northwest. What is unfolding today, however, is not the main event. It is merely the prologue. The part of this story that is not being widely discussed outside of meteorological circles is what comes next. Over the course of the next 120 hours, the same atmospheric system, generating those 5 mile per hour gusts in the northern Rockies, will undergo a profound reorganization across the entire lower 48 states. This system is projected to slide eastward, deepening into a closed low of 995 millibars over Kansas by 1:00 p.m. on Sunday. As it does, it will draw a massive plume of moisture northward from the Gulf of Mexico, feeding a warm sector larger than anything the plains have experienced since April. This will set off a chain reaction, delivering 4 consecutive days of escalating severe weather. The sequence is forecast to culminate in an event so significant that the Storm Prediction Center has already issued a Day 6 slight risk area stretching from Texas all the way to Wisconsin. To fully grasp the gravity of this forecast, one must understand the language of the Storm Prediction Center. The Day 4 to Day 8 outlook is typically the part of their forecast suite that acts as a long-range scratchpad. It is where meteorologists note areas where severe weather might be possible, with the full understanding that such long-term predictions are often uncertain. Therefore, the posting of a defined slight risk area 6 days in advance is an exceptionally rare occurrence. It is the meteorological equivalent of a surgeon informing you of a specific, definite complication a full week before your procedure has even begun. This level of certainty, this far out, is something that should not be possible under normal circumstances. And yet, the forecast is there, posted today, covering a vast region from Texas to Wisconsin. It is crucial to understand that what we are about to witness is not a series of separate, unrelated weather events. Instead, this is a single, coherent reorganization of the atmosphere happening in real time. The fire weather today, the hail tomorrow, the supercells on Friday, the outbreak on Saturday, the even larger outbreak on Sunday, and its extension into the Great Lakes on Monday. All of it is being propelled by the very same trough. It is all part of one unfolding narrative. As we delve deeper into the mechanics of this system, the goal is to understand not just what will happen this week, but why it is happening. This exploration may shed light on the underlying state of our atmosphere right now, because the most unsettling possibility is that this is not just a single, extraordinary week. It could be the beginning of a much longer, more active phase. Let us first examine the events of today, as they provide the proof of concept. The data from today is what gives us confidence that the rest of the forecast is grounded in reality. This morning, the Storm Prediction Center released its Day 1 convective outlook, which highlighted 3 distinct areas of severe weather risk. Each one tells a different part of the atmospheric story. The first is a marginal risk across the mid-Atlantic, situated ahead of a surface cold front that is sweeping across Ohio. This represents a relatively standard setup for frontal severe weather. A narrow corridor of convective available potential energy, or CAPE, is present ahead of the boundary, creating the possibility for damaging winds and isolated hail as the line moves through West Virginia and western Pennsylvania later this afternoon. The second area is another marginal risk over the Texas Panhandle. Here, a dry line is becoming established in temperatures climbing well into the 90s, while a thin envelope of moisture attempts to build just enough CAPE for 1 or 2 storms to ignite late in the day. But it is the third risk area that truly commands attention, as it involves a threat not commonly associated with classic severe weather outbreaks. This is the slight risk covering central Montana, eastern Idaho, western Wyoming, and northern Utah. The Storm Prediction Center is calling for damaging wind gusts in the 75 to 85 mile/hour range, produced within what is known as an inverted V-sounding environment. This setup allows for high-based, fast-moving showers and occasional thunderstorms to develop in a region that is exceptionally dry today, with boundary layer relative humidity in the single digits. This is not the plains. This is the northern Rockies. And the primary threat is not tornadoes, but something meteorologists call a dry microburst. This phenomenon involves a descending column of air, cooled by evaporation, which accelerates through a deep, dry layer below the cloud base. Upon hitting the surface, this column of air fans out in all directions at speeds comparable to a lower-end EF1 tornado. The immense danger lies in the fact that this microburst will impact a landscape where every blade of grass is tinder dry, a condition perfectly described by the inverted V sounding. And the reason the SPC's forecast is so specific and so concerning. When a thunderstorm forms over an environment with a deep, dry layer of air beneath it, a curious and dangerous process begins. Any precipitation falling from the storm evaporates long before it can reach the ground. This evaporation has a profound cooling effect on the air it touches. Because cold air is denser than the warmer air surrounding it, this newly chilled pocket accelerates downward under the pull of gravity. By the time this air mass strikes the surface, it can manifest as a powerful downdraft, with winds strong enough to overturn semi-trucks, snap power lines, and fell trees. But it is the final element of this process that truly matters. These storms can ignite fires. This happens because the same downdraft that carries the destructive wind also delivers lightning. The sparks strike fuel beds where soil moisture languishes in the bottom 10th percentile, in a landscape where the fire season is already 6 weeks ahead of schedule. It's a scenario so concerning that the National Interagency Fire Center has declared preparedness level 2 approximately 20 weeks earlier than the climatological average. The rarity of this combination cannot be overstated. Lightning striking in conditions so dry that no rain follows to extinguish the initial spark. It is a thunderstorm that produces all the sound, light, and wind of a storm, but not enough precipitation to even dampen a piece of paper. The Storm Prediction Center has a specific name for this phenomenon, an isolated dry thunderstorm, or IDRT. Today, the forecast map shows the IDRT zone sitting directly over the area, also marked for a slight risk of severe weather. It is the same mass of air, the same atmospheric trough, and the same physical mechanism at work. The very convection that generates the powerful wind gusts is also what produces the ignition source. This is precisely the kind of event that can lead to catastrophic wildfires. We need only look to the Smokehouse Creek fire in the Texas Panhandle in February of 2024, which became the largest wildfire in Texas history and the second largest in the history of the United States. In just 12 hours, that fire consumed 500,000 acres, driven by 60 mile-per-hour winds and single-digit relative humidity, with no rain in sight. This is the exact atmospheric configuration appearing on the map this afternoon across the northern plains. A more local, but equally chilling, parallel for this region is the Marshall Fire, which devastated Boulder County, Colorado, in December of 2021. That fire was propelled by wind gusts reaching 110 miles per hour, ultimately destroying 1,084 homes. The fire weather conditions that day were so unusual that they didn't even meet the criteria for a red flag warning at the time, because those criteria had not been written to account for a winter fire of such scale. While the rules have since been revised, the Marshall Fire serves as a stark cautionary tale. When extreme wind meets exceptionally dry fuel, a fire can grow faster than anyone in its path is able to escape. The gravity of the current situation is reflected in the official forecasts. The National Weather Service office in Bismarck, North Dakota, issued a hazardous weather outlook containing a red flag warning for today, followed by a fire weather watch for Thursday and Friday. This represents a 3-day forecast of consecutive critical fire weather conditions, posted during a part of the year when the fire season should not even be active. Meanwhile, the office in Twin Cities, Minnesota, looking at the same atmospheric data, noted that Friday's conditions are expected to be a near repeat of what they experienced on Tuesday, which was already a critical fire weather day. The pattern is clear. Today is a reload of the same dangerous configuration, and Friday is projected to reload it once more. 3 days, one trough, one atmosphere, and a tragically similar outcome each time. This repetition reveals that the atmosphere is locked into a persistent pattern, where the same forcing mechanism produces the same result over and over again. This is the signature of a Rossby wave packet, a vast, planetary-scale undulation in the upper-level airflow that has become quasi-stationary. The pattern is simply not moving fast enough to disperse its energy. The same trough situated over the west today will redevelop in roughly the same position tomorrow, reload on Friday, and then reorganize on Saturday for an entirely different yet related purpose. Saturday is when the trough is forecast to phase with a southern stream feature, causing the entire setup to pivot. The dry, high-based, fire-starting convection of today will give way to a deeply moist, Gulf-fed environment over the central plains. In a remarkable transformation, the very same trough producing dry microbursts in Montana today is the one that will likely produce 6-inch hail in Kansas on Saturday. The physics behind this evolution is a fundamental process of mass conservation. As the upper-level low deepens and strengthens, it must pull air upward from the surface to fill the space below. This powerful upward motion lifts the warm, moist air from the lower atmosphere. As that air rises, it condenses, releasing latent heat that causes it to accelerate further upward. This condensation builds thunderstorms, which are then organized by vertical wind shear. The mechanism is identical to what is happening today in the northern Rockies. The only difference is the moisture. Today in Montana, there is almost no moisture available, so precipitation evaporates before it can reach the surface. But by Saturday, the moisture will be there. The Gulf of Mexico will be open for business. The dry line will be sharply defined, and the storms that ignite along it will not be dry microburst factories. They will be moisture-charged supercells with rotating updrafts, carrying ice in their tops the size of softballs. This is the central idea to hold on to as this atmospheric story unfolds. The trough is a single feature, and the atmosphere is one interconnected system. The fire weather today is not a separate event from the hail on Saturday or the tornadoes on Sunday. It is the same atmosphere, expressing itself differently in different locations as the distribution of moisture and the upper-level dynamics evolve. By the time we reach Sunday, every ingredient that is missing from today's setup will be present, leading to the climax of this 5-day pattern. But before we move on, it is worth noting one more thing about today's events. They serve as tangible proof that the atmospheric models are not overstating the system's potential. For nearly a week, both the European and GFS models have been forecasting today's wind event in the Northern Rockies. The Storm Prediction Center's outlooks consistently flag this risk 3 and 4 days out. When a model forecast verifies with such accuracy days in advance, it builds confidence that the rest of the forecast cycle is also trustworthy. When a forecast for day 1 aligns perfectly with a prediction made 4 days prior, it lends significant credibility to subsequent long-range outlooks. This is precisely the situation we face now, as the Day 6 forecast indicates a slight risk for severe weather on Monday, the 18th of May, 2026. This risk area, stretching from Texas all the way to Wisconsin, is a signal of remarkable confidence. It is important to grasp the weight of this announcement. The Storm Prediction Center does not issue a Day 6 slight risk lightly. In fact, fewer than 30% of their outlooks contain any risk area at all. For one to span such a vast region, from the Gulf Coast to the upper Midwest, is rarer still. When forecasters signal a threat of this magnitude, nearly a week in advance, they are communicating a high degree of certainty in the model data. This is the foundation of our story, transforming what follows from mere speculation into a well-supported narrative. At this very moment, a single weather system is producing 2 entirely different threats across the country. This reveals the complex nature of our atmosphere. In the west, across Montana, Idaho, Wyoming, and Utah, the dry sector of a large trough is fueling dangerous fire weather conditions. Simultaneously, far to the east, an upper-level cold front associated with the same trough is sweeping over the Great Lakes and into the upper Ohio Valley. This is generating a band of frontal showers and a marginal risk for severe thunderstorms in parts of Pennsylvania, West Virginia, and western New York. It is a powerful illustration of how one atmospheric driver can produce hazardous weather on opposite sides of the continent. While these dual threats unfold, NASA's FIRMS satellite system has already detected 653 active fire hotspots across the lower 48 states in just the last 24 hours. This number is a baseline, a starting point established before the forecast, high winds, dry lightning, and new storm developments have even begun. This starting line is already 3 times higher than the climatological average for the second week of May, painting a sobering picture of the conditions at hand. This is the challenging scenario facing the Storm Prediction Center today. It is the reason that National Weather Service offices from Bismarck and the Twin Cities to Denver and Salt Lake City are issuing simultaneous warnings. It is a reality confirmed by the consensus among premier forecasting models like the ECMWF, the GFS, and the GEFS ensemble. And every single one of these elements is merely the opening act for a much larger event. For those living in Montana, Wyoming, Idaho, Utah, northern Colorado, the Dakotas, and Minnesota, practical preparations are paramount. Ensuring gutters are clear, Vehicles are parked away from trees, and a fire emergency kit is accessible in your car rather than the garage, are crucial steps. While today's wind event is expected to subside by midnight, tomorrow will bring a different story to another part of the country. Before we move forward, let us establish the central question this narrative will answer. I have stated that all of this week's weather is part of a single, unified pattern, with the same trough influencing events from today through Sunday and Monday. But the question remains, why? Why is this trough so unusually amplified? What gives forecasters such high confidence in a day 6 outlook? Why is the European model predicting a 995 millibar surface low over Kansas in mid-May? A pressure deepening that is a full standard deviation below the climatological norm? And how can the same week produce fire weather, a tornado outbreak, a G2 geomagnetic storm visible as far south as New York, and a heat dome bringing temperatures into the 90s to Kentucky and Virginia? The answer to all these questions is one and the same. For now, it is enough to understand that the atmosphere is not in a stable state. It is undergoing a fundamental phase shift. The Rossby wave that has governed North American weather for the past 3 weeks is reorganizing. An old pattern of a western ridge and eastern trough is collapsing, making way for a new pattern of a western trough and eastern ridge to build. When a planetary scale Rossby wave transitions like this, the result is exactly what we are witnessing: simultaneous, multi-hazard, continental scale weather extremes, all driven by the same underlying dynamics. The fire today, the hail tomorrow, and the tornadoes on Sunday are not separate stories. They are chapters of the same story, told across 5 consecutive days. Chapter 1 is today, as the atmosphere awakens from its previous state. Part 2 of our story sees the return of hail to Kansas. By Thursday morning, the trough responsible for today's fire weather in Montana will have shifted east and reorganized. The dry side of the system will be behind us, allowing moisture to flow into the central plains. Here, the first piece of our central narrative, a slow, deliberate escalation towards Sunday's outbreak, will begin to take shape. The Storm Prediction Center's Day 2 outlook already highlights a slight risk for severe thunderstorms across central and eastern Kansas, with the bullseye centered over Wichita, Manhattan, and Topeka. An analysis of the forecast soundings reveals a configuration that experienced plains forecasters would recognize instantly. A mid-level shortwave ridge is pushing into the upper Mississippi Valley, while a more subtle shortwave trough follows behind it from the Great Plains. Beneath this upper-level arrangement, surface dew points are climbing into the 60s Fahrenheit across eastern Kansas. Forecasters anticipate mixed-layer CAPE values between 1,000 and 2,000 joules per kilogram. 0 to 6 kilometer bulk shear around 40 knots and mid-level lapse rates near 8 degrees Celsius per kilometer. If these technical terms are unfamiliar, their meaning in plain language is what truly matters. CAPE, or convective available potential energy, is the fuel for a storm, the buoyant energy available to a rising parcel of air. A value of 1,000 to 2,000 joules per kilogram is more than sufficient to support the development of supercell thunderstorms. Bulk shear, the difference in wind speed and direction with height, is the ingredient that allows a storm to rotate. 40 knots is enough to generate rotating updrafts. Finally, lapse rates measure how quickly temperature cools with altitude. Steep lapse rates, like the 8 degrees Celsius per kilometer expected in the mid-levels, indicate unstable air that wants to rise rapidly, a key factor in producing hail the size of golf balls. When you combine these 3 distinct parameters, abundant fuel, sufficient rotation, and steep lapse rates, the result is a forecast for supercells capable of producing very large hail. This is precisely what Thursday is expected to bring to Kansas, making the hail threat the dominant story of the day. This morning, the Storm Prediction Center's discussion highlighted a significant threat: the possibility of hailstones exceeding 2 inches in diameter from any intense supercell. To put that in perspective, 2-inch hail is the size of a hen's egg, while 3-inch hail approaches the size of a baseball. Forecasters and storm chasers are focusing on a particular storm arrangement known as the discrete supercell mode, where storms develop as isolated individual cells rather than a continuous line. It is this very configuration that is notorious for creating the largest hail and the most violent updrafts. When a supercell can stand alone, free from competition for moisture from neighboring storms, its internal updraft can accelerate to an astonishing 30,000 feet per minute. This is more than powerful enough to suspend ice in the cloud until it grows to the size of softballs. The forecast for Kansas on Thursday anticipates exactly this scenario, with 2 or 3 such discrete supercells, each a powerful storm engine charting its own course across the landscape. While enormous hail is the foremost concern, the powerful mechanics that create it also produce damaging winds. The forecast includes the potential for outflow gusts reaching up to 70 miles per hour. There is also a conditional tornado threat, though it is being held in reserve because a key atmospheric component is not yet in place. The low-level shear in the environment is not currently strong enough to reliably support the formation of tornadoes, a fact that significantly alters the nature of the immediate danger. The missing ingredient for Thursday's storms is the low-level jet. This is a swift current of wind that typically forms at night over the plains at an altitude of roughly 5,000 feet, or 850 millibars. The low-level jet serves 2 critical functions for severe weather. First, it acts as a conveyor belt, drawing warm, moist air north from the Gulf of Mexico to provide fuel for the storms. Second, it increases low-level wind shear, which is the specific ingredient that allows a supercell's rotation to extend down to the surface and form a tornado. On Thursday, this low-level jet is forecast to be weak. For this reason, the Storm Prediction Center is not projecting a significant tornado risk. The necessary wind shear will exist, but it will be in the wrong vertical layer of the atmosphere to be effective. As a result, hail will fall and winds will gust, but the storms are unlikely to rotate tightly enough near the ground to produce the kind of tornado activity that will define the weather narrative later in the week. As we move into Friday, the pattern begins to evolve. The slight risk for severe weather continues across the central plains, but its focus shifts slightly eastward, with the bullseye moving toward Kansas City. A marginal risk extends to include St. Louis, Oklahoma City, Tulsa, and Springfield, Illinois. The atmosphere is essentially reloading, with another 2 to 3 discrete supercells expected to ignite along the dry line. Once again, very large hail remains the dominant threat, with the SPC's discussion specifically mentioning hailstones greater than 2 inches as the primary hazard, alongside isolated wind gusts of up to 70 miles per hour. The crucial change on Friday is the behavior of the low-level jet. It is forecast to intensify modestly compared to Thursday. While this is not enough to create a widespread tornado threat, the significant tornado parameter values in the forecast remain low. It is enough for a conditional tornado risk to emerge within a specific corridor just north of Kansas City. This narrow zone, running from Kansas City northeast through St. Joseph and toward the Iowa border, is where the strongest low-level helicity values are predicted. Helicity is the parameter that measures the atmosphere's potential to support rotation that reaches the ground, making this a region to watch closely. For anyone living in that corridor, including Kansas City, St. Joseph, Topeka, and Lawrence, Friday is the day when this conditional tornado threat becomes most relevant. Although the overall probability is low, it is wise to be prepared. This means having your phone on with weather alerts enabled and knowing your shelter plan. The reason for this vigilance is not that a tornado is likely, but that if one were to form in this environment, it would likely be embedded within a supercell, also producing baseball-sized hail and 7.0 mph winds. The combined impact of these hazards is something no one should face in a mobile home or a vehicle on the highway. It is in the day-by-day progression of this event that the overarching narrative truly comes into focus. Thursday is Kansas. Friday is Kansas. Saturday is Kansas again. By Sunday, the threat expands to include areas north and south, and on Monday, it stretches from Texas all the way to Wisconsin. This slow eastward drift, reloading over the same general region for 4 consecutive days, is the telltale signature of a slow-moving, deep-layer cyclonic system. We can see all the classic elements at play. The storm track is the plains, the fuel is moisture from the Gulf of Mexico, the trigger is the dry line, and the escalating danger comes from the gradually strengthening low-level jet. To understand the potential of this unfolding event, it helps to place it in a broader context, recalling a similar setup covered here on Calm Space. Last month, between April 12th and 14th, a comparable atmospheric configuration led to a significant outbreak, which we detailed in a previous video. That event produced widespread large hail and was responsible for an EF4 tornado in Enid, Oklahoma, and an EF3 in Mineral Wells, Texas. During that April outbreak, the low-level jet reached a maximum strength of approximately 25 to 30 knots, providing a crucial benchmark. The current forecast for this Sunday, May 17th, shows a low-level jet projected to reach 30 to 40 knots. This represents a meaningful step up from the April configuration. In practical terms, this suggests that Sunday's setup has the potential to be more violent than the April outbreak, with stronger surface-based rotation and a higher ceiling for tornado development. Thursday and Friday, in this context, are the build-up. These first 2 days represent the atmosphere preparing for a larger event. We see the warm sector slowly inflating, dew points climbing, low-level moisture deepening, and lapse rates steepening. It is a slow, methodical process of the atmosphere gathering its strength. By Friday evening, the storms that form over Kansas and Nebraska will begin to move east into the Mississippi Valley overnight. Forecasters note that these storms are expected to become elevated, meaning they will draw their energy from mid-level moisture rather than from the surface. As this happens, the severe risk will gradually decrease through the night. Saturday morning will bring a brief period of quiet as the atmosphere resets. Then, on Saturday afternoon, the entire setup is expected to pivot, beginning the next, more intense phase of this weather event. To truly grasp the significance of the weather unfolding this Thursday and Friday, we must first step back and examine the larger forces at play. The events of the coming days are not isolated, they are part of a much grander narrative. For those following our journey on Calm Space, you will recognize a recurring theme we have been tracking for weeks: the development of the next El Niño cycle. We recently explored the most severe spring drought in the United States' modern instrumental record. Days ago, we delved into the M5.7 solar flare from active region 4,432 and its consequences. And 2 weeks prior, we analyzed a CFSV2 model plume which projected the Niño 3.4 anomaly for December 2026 at a remarkable plus 2.9 degrees Celsius, with some members exceeding plus 3 degrees. This powerful signal that the Pacific is preparing for a super El Niño in the 2026 to 2027 winter has been a central thread since our April 23rd exploration of the 1,877 historical analog. This morning brought a pivotal update from the National Oceanic and Atmospheric Administration's Climate Prediction Center, and its latest oceanic Niño index. The value for the February-March-April 2026 period registered at plus 0.11. While this number seems small, its importance is significant. For the first time in over a year, the ONI has crossed into positive territory. The official threshold for an El Niño is a sustained value of plus 0.5 over 5 consecutive 3-month periods. So we are not there yet. However, the trajectory is what truly matters. The sequence over the last 6 months reveals a clear warming trend, from negative 0.55 to negative 0.54, then negative 0.37, negative 0.15, and now to plus 0.11. This represents a clean progression from a moderate La Niña through neutral and now beginning the climb toward El Niño conditions. It is a subtle shift, but one with profound implications. So, what does this gradual warming in the distant Pacific Ocean have to do with hailstorms developing over Kansas? The answer is, quite simply, everything. The amplifying trough over the western United States, the reorganizing upper-level flow, and the surge of an unstable air mass across the plains on Sunday are all connected. The specific wind shear environment that will support the formation of discrete supercells is also, in part, a downstream consequence of the Pacific's transition out of La Niña. Atmospheric patterns over North America during a developing El Niño are markedly different from those during a La Niña. In a La Niña phase, the polar jet is typically strong over the Pacific Northwest, causing storm systems to dive southward. But during the transition toward El Niño, the subtropical jet activates, allowing storm systems to phase more potently with southern stream energy. This is precisely the dynamic that fuels the Central Plains cyclogenesis we are about to witness. Looking back through history, we find this is the same Pacific dynamic that gave rise to the 1877 to 1878 Super El Niño. This catastrophic event, documented by the historian Mike Davis in his book Late Victorian Holocausts, was responsible for an estimated 30 to 60 million deaths globally from widespread monsoon failures, droughts, and resulting famines. This is not a fringe comparison. The 1877 event is the specific historical analog that has been flagged as the most relevant comparison by leading institutions, including NOAA's Climate Prediction Center, the European Center for Medium-Range Weather Forecasts, the World Meteorological Organization, and the climatologist James Hansen. The past, it seems, is offering a stark warning for our present. Yet, there is a critical difference between then and now. As noted by Zeke Housefather and the broader temperature reconstruction community, the planet has experienced a significant warming pulse since 2022. James Hansen attributes this acceleration to the International Maritime Organization's 2020 sulfur cap, which led to a reduction in marine cloud brightening aerosols. This has elevated the baseline global climate state by an estimated 0.26 to 0.56 degrees Celsius. What this means is that the same Pacific configuration that produced the 1877 catastrophe is now unfolding against a background climate that is already nearly half a degree warmer, raising unsettling questions about how this added heat will amplify the outcome. The timing of this week's severe weather pattern, reorganizing at the very moment the oceanic Niño index crosses into positive territory, is likely no coincidence. The atmosphere is actively reading and responding to the signals from the Pacific. A clear chain of causation is at work, running from the warming ocean to the upper-level flow, which in turn shapes the trough, the dry line, the supercells, and ultimately, the hail. It is crucial to see Thursday's hail not as an isolated storm, but as the first tangible product of a profound atmospheric reorganization that has been building since the start of the year. The recent drought, heat domes, and even last month's typhoon are all expressions of the same atmosphere reading the same ocean, just producing different outcomes based on regional geography. This week, that geography is the Central Plains. As we move forward, it is helpful to hold this central idea in mind. Our atmosphere is reorganizing on a timescale that operational meteorologists can measure in mere days. Yet, the underlying driver of this change is operating on a timescale that climatologists measure in months. The severe weather outbreak expected on Sunday will happen because the Pacific Ocean has spent the last 6 months steadily warming. This warming is occurring because the post-La Niña recovery is now underway, which itself is happening because the multi-decadal climate state has shifted into a configuration that favors more rapid El Niño transitions. The deeper reasons for that shift are part of the longer story Calm Space has been exploring. Thursday and Friday's weather, then, serves as tangible proof that this large-scale reorganization is real and is happening now. These are the days the atmosphere reveals its hand. We will see 2 days of Kansas hail, 2 days of supercells, and 2 days defined by warming dew points, steepening lapse rates, and a slowly strengthening low-level jet. This is the prelude. Then, on Saturday afternoon, the pattern fully consolidates into something much larger. The dry line will sharpen into a continental scale feature, and the warm, unstable sector will inflate, stretching from the Gulf Coast all the way to the Canadian border. The atmosphere will shift from building potential to releasing it. By Saturday afternoon, the trough that began its journey over the Pacific Northwest will have migrated east. A closed low will have organized over the Rockies, and the plume of Gulf moisture will have reached its maximum northward extent. With a sharp, dry line, dew points climbing into the upper 60s and low 70s, and Cape values approaching 3,000 joules per kilogram, the stage will be set. The low-level jet will have strengthened into the 20 to 30 knot range, and we can anticipate that the Storm Prediction Center's Day 3 outlook for Saturday will be upgraded accordingly. A slight risk is currently in place, but conditions suggest this is only a preliminary assessment. There is a strong likelihood of an upgrade to an enhanced risk, and a meaningful probability exists that it could reach a moderate level by Saturday morning. The geographic focus for this event appears to be centered over Oklahoma and Kansas, with the area of concern extending northward into Nebraska and eastward into Missouri. The most dangerous period is forecast to be a 6-hour window from approximately 4:00 inches the afternoon to 10:00 inches the evening local time. During this time, the prevailing storm mode is expected to be discrete supercells forming along a dry line. The resulting threats are significant. The hail could be exceptionally large, capable of cratering windshields and denting car hoods. Widespread damaging winds are also anticipated. And for the first time this week, a conditional tornado threat, absent on Thursday and Friday, will become a distinct possibility. This shift occurs because by Saturday, the low-level jet will have gained sufficient strength, and the shear in the atmosphere will be primed for surface-based rotation. The discrete supercell structure, forecasted by the European model, means that any storm that ignites will have all the necessary ingredients, moisture, shear, and lift to produce a tornado. The situation on Sunday is projected to be even more severe, with Monday potentially marking the most significant day in the Storm Prediction Center's outlook for the entire week. But before we look ahead, it is crucial to understand the setup for Saturday, as this is the day the pattern transitions from a period of build-up into a full-blown outbreak. While Thursday and Friday serve as warning shots, Saturday represents the first true volley in this severe weather episode. Sunday may be the climax, and Monday the encore, but Saturday is where the atmospheric transformation is truly unleashed. For 5 days, the pattern has been reorganizing. A trough has journeyed from the Pacific Northwest to the Rockies. The Gulf of Mexico has opened up to send moisture northward. The dry line has sharpened, and the warm sector has expanded. The same atmospheric forces generating wind gusts in the mountains today are set to produce the first major severe weather outbreak of May 2026 by Saturday evening. Let's examine what the European deterministic model projects for the afternoon of Saturday, the 16th of May, 2026. A new closed low is shown developing over the Rockies. As the trough digs southward, a feature from the southern stream begins to phase in from the desert southwest. This phasing process triggers explosive cyclogenesis, causing the surface pressure to drop rapidly. By late Saturday afternoon, the surface low will be intensifying over the southern high plains. A powerful engine for the storms to come. A sharp dry line will establish itself, oriented north to south from the Texas Panhandle into western Kansas. East of this boundary, dew points will be in the upper 60s to low 70s, while to the west, they will plummet into the 30s and 40s. This stark contrast is the key. The dry line acts as the trigger, representing the boundary between different air masses and serving as the most reliable mechanism for initiating severe weather in the spring climatology of the plains. As the dry line mixes eastward during the afternoon, convergence develops along the boundary. Once the atmospheric cap, a temperature inversion that holds back premature storm development, finally breaks, the storms will fire with explosive force. When storms erupt along a dry line in the late afternoon, within a moisture field this large and unstable, they almost invariably form as discrete supercells. This particular storm configuration is responsible for producing the most violent tornadoes and the most giant hail. Historically, these are also the storms that drive the largest insurance loss events in the modern severe weather record. The reason for their destructive potential lies in their isolation. By definition, discrete supercells are not embedded in a continuous line. They do not have to compete with neighboring storms for the same inflow of moisture. They enjoy unrestricted access to the warm sector, allowing them to rotate freely. Their updrafts can soar to 40,000 feet, their hail growth zones can operate without interruption, and their low-level mesocyclones can tighten and intensify without being disrupted by the outflow from an upstream storm. It is a portrait of terrible efficiency. For the Saturday environment, the model forecasts make this discrete supercell mode a near certainty. The atmospheric lift along the dry line is forecast to be strong but localized. The cap is significant, but not so strong that it cannot be overcome. The wind shear profile is highly favorable for rotation. Cape values are high, and storm initiation is expected to occur in a narrow corridor. This, combined with widely spaced storm motion, will allow each cell to mature independently into a powerful, self-sustaining system. The bullseye on Saturday will be centered somewhere over Oklahoma and Kansas. The I-35 corridor, which runs from Dallas-Fort Worth through Oklahoma City and Wichita up to Kansas City, lies directly in the heart of this risk area. The threat will extend as far north as Nebraska and as far south as the Red River. The western edge will be sharply defined by the dry line itself, which by Saturday afternoon will have positioned itself somewhere between Amarillo, Texas, and Liberal, Kansas. The Storm Prediction Center's current Day 3 outlook for Saturday already indicates a slight risk. The general expectation is that the Day 2 outlook will see an upgrade to an enhanced risk, which is a level 3 out of 5. There is also a non-trivial probability that by Saturday morning, the Day 1 outlook will feature a moderate risk, level 4 out of 5, for the immediate bullseye. Moderate risk days are rare and are issued only when forecasters have very high confidence in widespread, significant, severe weather. The potential for such an upgrade underscores the gravity of the situation. The window for the most intense storms will be from roughly 4:00 p.m. to 10:00 p.m. local time. This is when daytime heating peaks, the cap fully breaks, and the dry line-driven convection ignites. Once these storms fire, they will quickly mature into rotating supercells. The hail growth within these updrafts is expected to produce hailstones in the 2 to 4 inch range, from the size of golf balls up to baseballs. In the most intense cells, there is a possibility of stones exceeding 4 inches in diameter, the size of softballs. To put this into perspective, a 2-inch hailstone falls at about 70 miles per hour, while a 4-inch hailstone reaches a terminal velocity of approximately 100 miles per hour. A softball-sized hailstone will not just crack a windshield, it will go through it. It will leave significant dents in the hood of a vehicle and can be lethal if it strikes a person. This is the nature of the threat on the table for Saturday afternoon, and it runs parallel to a significant wind threat. When discrete supercells reach the end of their life cycle, they often collapse, unleashing powerful downdrafts. Depending on their specific structure, meteorologists refer to these phenomena as wet downbursts or rear flank downdrafts. The atmospheric environment on Saturday is expected to support peak gusts within the 70 to 90 mile per hour range from the most intense cells. Such winds carry enough force to snap power poles, a description used by the Storm Prediction Center itself, and to fell mature trees across a significant area. It is a stark reminder of the raw, kinetic energy contained within these formations. The most consequential and yet most uncertain aspect of Saturday's forecast is the potential for tornadoes. The Storm Prediction Center's discussion notes that this threat is conditional. This means the formation of tornadoes hinges on whether the supercells can remain isolated enough to develop and sustain rotation at the surface. If the storms stay discrete, tap into the intensifying low-level shear, and if the atmospheric cap breaks cleanly, then a few tornadoes are indeed a distinct possibility. This outcome is favored by the European model's deterministic run and supported by the Jeffs Ensemble tornado parameter forecasts. An alternative scenario would limit the tornado threat. If the dry line mixes eastward more slowly than anticipated, or if a mid-level cap persists, the storms might be forced into a more linear formation. In that case, the primary danger would shift to large hail and damaging winds, with a reduced tornado risk. However, the current model signals point toward the discrete storm scenario, and that is the basis for the SPC's forecast. For residents in a corridor that includes Oklahoma City, Topeka, Wichita, and Kansas City, as well as Norman, Stillwater, and numerous other communities along Interstate 35, Saturday is a day that demands prior preparation. The time to ensure a storm plan is in place is now, not on Saturday morning. The forecast is solidifying. The Pacific Northwest trough that is driving this event is verifying against the models, and the Day 3 outlook is already clearly defined. The escalation of risk is tangible. As a testament to this, storm chasers are already moving into position. This community relies on high-resolution model data to make their decisions, and the output for the planes is signaling a major event. The unusually high number of chase teams expected this weekend is, in itself, a powerful signal. When seasoned observers believe an event has the potential to produce significant tornadoes, they converge. To understand the full scope of Saturday's threat, we must place it in a wider context. Our ongoing analysis has been tracking the worst spring drought in the modern instrumental record across the United States. Because of these drought conditions across the plains, any rain that falls on Saturday will likely run off instead of being absorbed. The soil is baked hard and the vegetation is stressed. While discrete supercells typically move too quickly to produce widespread flooding, they deliver intense rainfall in narrow corridors. This precipitation will fall onto ground that simply cannot take it in. Consequently, the threat of flash flooding will be localized but very real, particularly along stream corridors and in low-lying areas that happen to fall under a storm's path. The Storm Prediction Center's own discussion contains a crucial insight, noting that the impending threat is being driven by the very same trough that is currently producing dry microbursts in Montana. This single sentence, buried within the Outlook discussions, may be the most important key to understanding the entire week's weather. It is an explicit acknowledgement that these seemingly separate events are all connected, all driven by a single, vast atmospheric feature. The trough active today is the same one that will be active on Saturday, Sunday, and Monday. While the geographic location of its impacts will migrate, the underlying atmospheric driver remains constant, telling a story of a single, unfolding dynamic system. Another piece of essential context is the broader weather pattern developing across North America. While the plains brace for a severe outbreak, the East Coast is beginning to feel the initial signs of a rebuilding heat dome. By Sunday and Monday, this dome of high pressure is forecast to be firmly established over the mid-Atlantic and the southeast, bringing temperatures in the upper 80s to mid-90s to states like Kentucky, Virginia, and the Carolinas. The same atmospheric mechanism, a trough ridge phase shift that produces the plains outbreak, is also responsible for rebuilding the heat dome to the east. As the trough digs into the west, the ridge to its east re-amplifies. It is a perfectly coupled system, an illustration of a Rossby wave reorganization in motion. This represents a fundamental shift in the continental pattern. The western ridge and eastern trough configuration that dominated late April and early May has now collapsed. In its place, a new pattern has emerged, a western trough and an eastern ridge. This new alignment is the classic setup for severe spring weather in the plains and, simultaneously, the classic configuration for early summer heat along the east coast. Both effects are products of the same planetary wave shift, and both are unfolding this week. What makes this particularly noteworthy is the potential persistence of this new pattern. This Rossby wave reorganization may not be a fleeting change. Research, such as the 2021 Hanatal paper on low-phase speed Rossby wave packets, has shown that these quasi-stationary planetary waves can lock into place for 1 to 3 weeks. The previous western ridge was such a feature, and this new western trough may be as well. This raises a critical question. Could the severe weather corridor opening this weekend remain active well beyond Monday? Extended forecasts seem to hint at this possibility. The European model's ensemble forecasts show additional severe weather risk continuing through the end of May. Even the Storm Prediction Center's experimental Day 8 outlook, which is used cautiously, has suggested a continued elevated risk across the plains for the next 2 weeks. Forecasters calling this the most active stretch of severe weather of the year are doing so, in part, because they see a pattern that may persist. This is the longer arc of the story. Saturday is a single outbreak, but the week is a sequence of them, and this week may merely be the opening chapter of a much longer phase. The afternoon of Saturday, however, will be visceral and immediate. By 6:00 inches the evening, supercells will likely be on the ground from the Texas Panhandle northward into western Kansas. By 7:00, the most powerful of these storms will be capable of producing hail up to 4 inches in diameter, and the first tornado warnings will likely be issued. By 8 in the evening, storm chase teams will be deploying across the plains, tracking individual cells as they mature. At the same time, the local National Weather Service offices in Norman, Wichita, Topeka, Dodge City, and Amarillo will be in full coordination, issuing warnings in real time. The first verified tornadoes are anticipated to be reported by 9 o'clock. As the night progresses, the character of the storm system will begin to shift. The discrete supercell phase is expected to merge into a more linear structure, continuing its eastward march into the Mississippi Valley overnight. As the sun sets and daytime heating is lost, the inflow of energy to the storms diminishes, causing the nature of the threat to evolve. This transformation from isolated supercells to a nocturnal squall line is the natural, albeit dangerous, life cycle for these systems. The tornado threat reaches its peak during the discrete phase, while the risk of damaging wind persists into the linear stage, and the hail threat subsides as the storms move into a more sheared environment with shorter cell lifespan. By Sunday morning, the remnants of Saturday's system will have raced eastward into the lower Missouri Valley. The primary threat will then be advancing toward Arkansas, the Ozarks, and the lower Mississippi Valley. But the crucial detail is that the underlying atmospheric trough is not yet finished with its work. The trough will remain anchored over the central United States. The Gulf of Mexico will continue to supply abundant moisture, and the dry line is forecast to reform. The warm sector is projected to inflate once again, this time covering an even larger area. This sets the stage for Sunday, when the process of cyclogenesis is anticipated to be far more aggressive than it was on Saturday, raising questions about the potential for an even more significant event. The European model offers a stark projection. On Sunday, the surface low-pressure system is forecast to deepen to 995 millibars by 1:00 p.m. local time, with its center over Kansas. That 995 millibar figure is a critical data point. A low of this intensity over Kansas in mid-May represents a deepening of 1 standard deviation below the climatological mean for the period. While not unprecedented, it is precisely this kind of atmospheric deepening that history associates with major tornado outbreaks. It is a number that signals immense potential energy waiting to be unleashed. To fully grasp the gravity of a 995 millibar forecast, we can turn to the historical record. The devastating 4th of May 2007 Greensburg, Kansas, EF5 tornado occurred beneath a surface low that reached 992 millibars. The widespread 14th of April 2012 Wichita, Kansas tornado outbreak unfolded under a 994 millibar low. The forecast for Sunday, the 17th of May 2026, places the atmospheric setup in the same statistical family as these historical outbreak progenitors. This comparison is not a prediction of a specific outcome, but a measure of the storm system's potential. The purpose of this analysis is not to declare that Sunday will produce an EF5 tornado. Rather, it is to highlight that the surface configuration predicted by the European model resides in the same statistical range as the setups for past major outbreaks on the plains. This is precisely what the Storm Prediction Center is observing when it states that Sunday could be the most active severe weather day of May 2026. They are looking at a model forecast that places the impending cyclogenesis in the same category as historical outbreak events, and they are expressing this high level of concern publicly, a full 6 days in advance. There is also a layered threat that few are discussing yet. As Saturday's outbreak unfolds across Oklahoma and Kansas, Earth's geomagnetic field will be approaching the peak of a G2 storm watch. The forecast anticipates a peak KP value of 5.67 between 3 and 6 UTC on Friday, May 15th. This time frame corresponds to approximately 11 p.m. Central Daylight Time on Thursday evening, the very window when the first significant hailstorms are expected to impact Kansas. By Saturday morning, the geomagnetic disturbance will be waning. Throughout the afternoon and evening, as the plains outbreak intensifies, the aurora will settle over the northern tier of the country. This creates a moment of profound convergence. The northern lights, visible from New York, Wisconsin, and Washington on Friday evening, will fade as Saturday morning dawns. And, just as they fade, supercells will be igniting along a dry line 2,000 miles to the south. It is a powerful reminder that the same atmosphere reading the Pacific is also reading the sun. The very system producing tornadoes in Kansas is also allowing the solar wind to paint the sky over the Great Lakes. The same audience watching the storms from Oklahoma may look up on Friday night and witness the aurora. That is what convergence looks like. In the final part of our analysis, we will walk through the Sunday outbreak, the climax of this week, in extensive detail. We will explore the setup, the supercells, the squall line, the tornado threat, the additional flash flood layer, and the enormous geographic sweep from Oklahoma to Minnesota that is poised to define the headlines by Monday morning. But before we arrive at Sunday, it is essential to appreciate what is going to happen on Saturday. That day will generate its own news cycle, producing its own tornado reports, hail damage photos, and storm chase footage. Saturday is set to be a major severe weather day on its own considerable merits, and Sunday is forecast to be worse. Part 4. Sunday, the climax. This is the day the entire week has been building toward. The atmospheric trough that began its journey over the Pacific Northwest 5 days earlier, the one that produced a dry microburst in Montana, ignited the dry line, generated hail in Kansas on Thursday and Friday, and drove Saturday's discrete supercells. That same trough will reach its maximum amplitude on Sunday, May 17th. The European deterministic model resolves a surface low-pressure system at 995 millibars, centered over Kansas by 10 inches the afternoon, local time. The pressure gradient surrounding this low is projected to be the steepest the Central Plains have experienced in May 2026. On Sunday afternoon, the low-level jet is forecast to intensify to 30 to 40 knots, creating a powerful river of wind just above the surface. The band of strong low-level winds is expected to become incredibly elongated, stretching from Texas all the way into Minnesota and Wisconsin. This elongation is the single most critical detail. It is the factor that transforms a regional severe weather event into a continental scale outbreak. When the low-level jet forms a narrow band that extends for over 1,500 miles, the warm sector it nourishes becomes similarly elongated. The dry line that forms on the western edge of that warm sector is, in turn, also elongated. As a result, the convergence and storm initiation along that dry line become equally stretched out, causing supercells to fire across more than 1,000 miles of latitude. The outcome is an outbreak that produces severe weather not just in one state, but in 7 or 8 states simultaneously. This is the scenario the European model is forecasting, from Oklahoma and Texas in the south, extending north through Kansas, Missouri, Nebraska, Iowa, Illinois, Wisconsin, and Minnesota. The model indicates discrete supercells forming along the dry line on Sunday afternoon. By Sunday evening, these individual cells are expected to transition into a fast-moving squall line, a line capable of producing destructive straight-line winds exceeding 75 miles per hour as it moves east. By late evening, the storm system is expected to evolve into a line affecting cities like Des Moines, Cedar Rapids, and Omaha. This progression carries a layered threat, as repeated downpours could trigger flash flooding by depositing several inches of rain over the same locations in a very short period. To truly grasp the nature of this event, it is essential to examine its timing, which is just as critical as its geography. Sunday morning will dawn with a deceptive sense of peace across the Central Plains. This quiet, however, is not one of stillness, but of preparation. In the unseen realm of the atmosphere, a tremendous amount of energy will be accumulating. Dew points will steadily rise, and the low-level jet stream will intensify. Across Oklahoma and Kansas, surface dew points are forecast to reach the high 60s to low 70s, while CAPE values, a measure of atmospheric instability, are expected to build toward an explosive 4,000 joules per kilogram. A low-pressure system over western Kansas will continue to deepen, contributing to the oppressive, hot feeling outdoors. It is the kind of midday weather that naturally encourages one to seek shelter long before the storm itself arrives. The atmosphere's warm sector will be fully primed by mid-afternoon, around 2:00 to 3:00 p.m. local time. The next phase begins between 3:00 and 4:00 p.m., when the atmospheric cap, a layer of warm air that initially suppresses storm development, is expected to break along the dry line. This is the moment the atmosphere unleashes its stored energy. The first cumulus clouds will begin to ascend, quickly growing into towering columns. By 4:30 p.m., the first supercell will likely ignite on radar, and by 5:00 p.m., 3 or 4 distinct supercells could be churning across the central and southern plains. An hour later, by 6:00 p.m., these storms will have reached maturity. Hail will begin to fall, the first tornado warnings will be issued, and storm chase teams, having positioned themselves overnight, will be intercepting these cells in real time. Across the region, National Weather Service offices will enter a state of high-level coordination, issuing warnings as the supercells track across county lines. The epicenter for Sunday afternoon's most severe weather is anticipated to be a region stretching from central Oklahoma northward into central Kansas, with a possible extension into southern Nebraska. This specific area is the bullseye because it represents a rare convergence of atmospheric ingredients. Here, the strongest low-level shear, the steepest mid-level temperature gradients, the deepest moisture, and the most powerful lift along the dry line are all forecast to overlap. This alarming alignment is why the Storm Prediction Center's outlooks for Day 3 and Day 4 will be highlighting this zone. By Sunday morning, it is probable that the Day 1 outlook will designate an enhanced risk for this bullseye, with the potential for a moderate risk depending on morning atmospheric trends. The headline threat for Sunday will undoubtedly be tornadoes. The Significant Tornado Parameter, or STP, is a composite index that evaluates the potential for strong tornadoes of EF2 intensity or greater by combining metrics for instability, wind shear, and other atmospheric conditions. This index is projected to be elevated across the entire bullseye region. The European forecast model, for instance, is indicating STP values in the 4 to 6 range for central Oklahoma and southern Kansas on Sunday afternoon. Historically, numbers of this magnitude are strongly correlated with days that produce significant tornado outbreaks. The development of discrete supercells will be a critical factor. When these isolated, individual storms form within an environment characterized by high cape, powerful low-level shear, and steep lapse rates, they can produce violent tornadoes of EF3 intensity or higher. The outbreak on April 23rd, which generated the Enid EF4 tornado, occurred under similar conditions, though the low-level jet forecast for this Sunday is even stronger. This combination of factors makes the environment more favorable for violent tornadoes than what was seen during the April event. This, of course, does not guarantee a violent tornado will form. Tornadogenesis is a stochastic process, and even in the most primed environments, not every storm will produce one, but the potential is undeniably there. To understand what is truly at stake, it is important to comprehend the power represented by the enhanced Fujita scale. An EF3 tornado, with wind speeds of 136 to 165 miles per hour, can destroy well-built homes, tear off roofs, lift cars from the ground, and strip the bark from trees, leaving a damage path hundreds of yards wide. An EF4 tornado, with winds between 166 and 200 miles per hour, can level houses, hurl vehicles over long distances, and carve a path of destruction up to a mile wide. Above that, an EF5 tornado, with winds exceeding 200 miles per hour, produces damage that is almost beyond comprehension. It can sweep homes clean from their foundations, toss cars for hundreds of yards, and create damage paths that are miles across. The historical context for such events is sobering. The 2007 Greensburg EF5 tornado virtually erased the entire town of Greensburg, Kansas. In 2011, the Joplin F5 tornado resulted in 158 fatalities and over $3 billion in damages. And the 2013 Moore F5 tornado left behind one of the most photographed paths of devastation in recent memory. While Sunday's environment does not guarantee an EF5 indeed, most major plains outbreaks do not produce them. The conditions fall within the range where EF3 and EF4 tornadoes have historically occurred. Given the large geographic footprint of the outbreak, the probability of at least one EF3 or stronger tornado developing somewhere in the bullseye on Sunday afternoon is significant. The Storm Prediction Center's experimental tornado outlook will be tracking this probability in real time. For anyone living in central Oklahoma, central or southern Kansas, southern Nebraska, the Texas Panhandle, or along the I-35 or I-40 corridors in these states, Sunday is a day that demands a shelter plan. On Saturday night, before going to bed, it is crucial to prepare a shelter location with water bottles, a flashlight, a fully charged phone, and a battery-powered NOAA weather radio. Ensure your vehicle has a full tank of gas, you know the route to the nearest hospital, and your insurance information is in a portable format. It is also vital to have a plan that accounts for children, elderly family members, and pets. Regional emergency management officials will be in active monitoring mode throughout Sunday afternoon. As Sunday evening progresses, the nature of the storm will shift. The loss of daytime heating will cause the warm sector to cool, and the discrete supercells will begin to lose their isolated character. They will start to merge, forming a fast-moving squall line. This marks the second act of the storm event. The squall line will accelerate eastward at 50 to 60 miles per hour, and the primary threat will transition from tornadoes to widespread, destructive straight-line winds. This squall line, developing on Sunday evening, is forecast to track east into Iowa, Missouri, and Illinois through the overnight hours. The wind threat will be extensive, with widespread gusts potentially exceeding 75 miles per hour. Cities in its path include Des Moines, Cedar Rapids, Omaha, Davenport, and the Quad Cities, with the threat possibly extending east toward Peoria and Chicago overnight. By the time this line of storms reaches the Mississippi River early Monday morning, it will have likely left a trail of widespread wind damage across a corridor several hundred miles wide. Beyond the immediate dangers of wind and hail, the threat of flash floods adds another layer of complexity to this event. A particular concern is the potential for training downpours, a phenomenon where storms repeatedly pass over the same locations. These systems can unleash 3 to 5 inches of rain in just 2 to 3 hours. This presents a dangerous paradox, as this intense rainfall will fall upon soils currently experiencing the most severe spring drought of the modern instrumental record. Instead of being absorbed, the water will run off with incredible speed. This makes flash flooding a significant risk, especially within stream corridors and in urban centers, where drainage systems may be quickly overwhelmed. Local emergency officials will be vigilantly coordinating flash flood warnings through Sunday evening and into Monday overnight. To truly understand the significance of Sunday's events, we must step back and view them within a broader climate context. This is a more difficult part of the story, but one that is essential for a complete picture. On the surface, the atmospheric setup driving this outbreak appears to be a textbook configuration for severe weather in the plains during spring. It includes all the classic ingredients: a strong upper-level low, a sharp dry line, deep moisture, a powerful low-level jet, and steep lapse rates. Considered individually, none of these elements are unprecedented. What is truly unusual, however, is the combination of all these factors acting in concert against the backdrop of our planet's current climate state. This modern climate state is anomalous in several key ways. The Pacific Ocean is transitioning out of La Niña and into El Niño at a pace the World Meteorological Organization has called particularly rapid. In the Niño 3.4 region, the subsurface ocean heat content for April has reached the highest level ever recorded by satellites. Furthermore, a post-2023 warming pulse has elevated the global baseline climate state by an estimated 0.26 to 0.56 degrees Celsius. This pulse has been attributed by researchers like Hansen and Housefather to the International Maritime Organization's 2020 sulfur cap, which reduced marine cloud brightening aerosols. In response, atmospheric water vapor has increased, following the Clausius-Clapeyron scaling of about 7% for every degree of warming. All these factors are compounded by the worst drought in the modern record across the plains, and a fire weather calendar that is running 6 weeks ahead of climatology. These background conditions do not directly cause an outbreak like Sunday's, but they fundamentally alter the environment in which it occurs, elevating its potential. A 995 millibar low developing in a warmer, moister atmosphere is primed to generate more violent storms than the same low in a cooler, drier one. An identical low-level jet, when interacting with a higher dew point baseline, can support stronger and more persistent supercells. Similarly, a dry line pushing into air with more steeply sloping lapse rates can produce significantly larger hail. The atmosphere is simply following the laws of physics, but it is doing so within an environment that is progressively warmer, wetter, and more capable of producing extreme outcomes. This is what scientists mean when they speak of climate change loading the dice. The atmosphere is not creating entirely new types of storms. Instead, it is amplifying the storms that have always occurred. It is making the same severe weather outbreaks more violent, the same droughts more extreme, and the same heat waves hotter. And what is most striking is that it is doing all of this simultaneously, within a single week and a single hemisphere, as part of one coherent atmospheric reorganization. The 2022 Williams paper in Nature Climate Change, which we explored in a previous Calm Space video, used a 1200-year tree ring network to show that the period from 2010 to 2021 was the driest 2-year span in the American Southwest in 800 years. That study attributed 42% of the soil moisture deficit to anthropogenic climate forcing. An updated attribution study from CU Boulder in 2025 has since extended that signal forward in time. The drought we are witnessing now is part of that same long-term trend, and the atmospheric configuration producing it is the very same one that supports the plains outbreak on Sunday. The deep western trough driving this week's weather is a broader manifestation of the Rossby wave reorganization that is also producing the megadrought signal. The two phenomena are inextricably linked. The trough represents the acute event, a periodic pulse of extreme weather embedded within the chronic state of the long-term drought. Both are being intensified by the same background warming. This leads us to a more challenging version of this story. The Sunday outbreak is not merely an episode of severe weather. It is severe weather unfolding within a climate that has been steadily warming for decades. This warming is making our weather more violent, more frequent, and more compound. Every storm is now bigger than it would have been in a cooler climate. Every outbreak is more spatially extensive, every drought more severe, and every fire season starts earlier. Each heat dome becomes more amplified, and every reorganization of the Rossby waves produces more compound extremes. This is what makes the forecast for this Sunday so different from what a forecast for the same atmospheric setup would have looked like in 1960. That same trough in 1960 would have produced a smaller outbreak. The hail would have been smaller, the tornado paths shorter, and the resulting damage less severe. A drought from that era would be considered a wet year by today's standards. A fire weather day, like the one in the northern Rockies today, would have been unusual, but not unprecedented. Sunday's outbreak is being forged in a warmer atmosphere, and that atmosphere remembers everything. By Sunday night, the squall line will be racing eastward toward the Mississippi River. As it does, the nature of the threat will evolve. The tornado threat will begin to wind down, but the danger from high winds will persist. At the same time, the flash flood threat will reach its peak. The forecasters at the Storm Prediction Center will already be turning their attention to Monday. And Monday is when this system extends into the Midwest and the Great Lakes, completing its eastward sweep across the entire central United States. The outlook for Monday is perhaps the most telling part of this entire sequence. The Storm Prediction Center issued a Day 6 slight risk, a significant action taken 6 days in advance. The geographic footprint of this risk is enormous, stretching from Texas all the way north through Wisconsin, making it the largest risk area of the week. It is on this day that the central narrative that all of this week's events are part of a single, cohesive pattern becomes fully visible to any outside observer. By Monday, the squall line that first erupted over Oklahoma will be over Indiana, and the discrete supercells that left a trail of damage in Kansas will have moved on their journey, a testament to the scale and power of this system. As the new week begins, the remnants of Sunday's storm system will seem like a distant memory. The dry line that fueled the outbreak will have repositioned itself over Texas, and the cold front that passed through the northeast will be long forgotten. But the true engine of this entire weather event, the trough, will remain. It continues to amplify, to deepen, and to do what it has been doing all week long. On Monday, this system is poised to deliver one final, powerful performance before the atmospheric pattern at last begins to relax. This is the encore. But before we look ahead, it is worth pausing to consider what Sunday represented. The very same atmosphere that generated a dry microburst in Montana is the same one that is forecast to unleash a tornado outbreak in Oklahoma. The trough is the same. The atmospheric driver is the same. It is all one interconnected system, reorganizing itself before our very eyes. By Monday morning, a new day will dawn on a landscape forever changed. The squall line that erupted over Oklahoma on Sunday will have advanced to central Indiana, while the discrete supercells that spawned it will be gone. In Kansas and Oklahoma, headlines will be dominated by reports of hail damage, and the first aerial surveys will take to the skies to map the destruction. Local National Weather Service offices will shift into their post-event procedures, dispatching teams to assess the tornado paths and assign them EF ratings. At the same time, storm chasers will be packing their equipment, downloading footage, and sharing stories of what they witnessed. Yet while all this recovery and reflection takes place, the trough, the very same one that has orchestrated every event this week, is far from finished. The Storm Prediction Center's Day 6 outlook for Monday, the 18th of May, 2026, which has been a focus of our narrative, designates a slight risk for severe weather. What makes this forecast so remarkable is its sheer scale. The risk area extends from Texas through Oklahoma and Kansas and stretches north across Missouri, Iowa, Illinois, and nearly the entire state of Wisconsin. This places major metropolitan areas like Dallas, Oklahoma City, Kansas City, Sreet, Louis, Des Moines, Minneapolis, Milwaukee, and Chicago, all within the potential impact zone. A Day 6 outlook rarely covers such a vast territory, and the fact that the SPC issued it so far in advance speaks to the profound confidence forecasters have in this developing threat. It is the central anomaly of this week's forecast. So, what makes Monday's potential so significant? The answer lies in the evolution of the low-pressure system itself. Instead of weakening overnight as one might expect, it actually intensifies. The European forecast model shows the surface low deepening through Monday morning as the atmospheric trough completes its phasing. In fact, the upper-level dynamics are projected to become even more favorable for severe weather on Monday than they were on Sunday. This is because the cold front powering the convection will have finally caught up to the warm sector, creating a more aggressive zone of convergence. The dry line reforms over Oklahoma and Texas. The plume of moisture from the Gulf re-energizes, and the warm sector inflates once more this time, even larger than Sunday's, pushing farther north and east. The forecast models for Monday afternoon depict a setup that the Storm Prediction Center describes with sobering clarity. They anticipate an intense, low-pressure system producing widespread severe weather from Wisconsin back into Oklahoma and Texas. The agency's forecast includes the potential for widespread damaging winds, very large hail, and a significant strong tornado threat. This is the kind of language the SPC reserves only for those forecasts where there is high confidence in a major outbreak. The bullseye for this event will also shift. While Sunday's focus was on Oklahoma and southern Kansas, Monday's primary corridor of concern will be farther north, somewhere between Minneapolis and Kansas City, with a secondary zone running from Dallas-Fort Worth through Oklahoma City. This northward shift of the severe weather threat is a direct consequence of the low-pressure system's own movement. The closed low, which is forecast to bottom out at 995 millibars over Kansas on Sunday, will have migrated to a position over central Missouri or southern Iowa by Monday morning. As it moves, the warm sector ahead of it expands northward in tandem. The Minneapolis area on Monday is a particularly noteworthy example of this progression. For the first time this week, Minneapolis and the surrounding Twin Cities metro region will find themselves squarely in the warm sector. Dew points are expected to climb into the upper 60s and low 70s values that are quite uncommon for Minnesota in mid-May. The atmospheric instability, or CAPE, will be more than sufficient to support deep convection, while the wind shear will favor the development of supercells. Critically, the region's geographic position relative to the surface low places it in the classic warm sector, left mover position, a configuration historically associated with the most violent tornadoes. For residents in the Twin Cities metro, as well as in Eau Claire, Madison, Milwaukee, Rockford, Chicago, Cedar Rapids, and Iowa City, Monday is the day the outbreak arrives at their doorstep. The Storm Prediction Center is expected to issue numerous watches and warnings throughout the afternoon and evening across a region that historically does not experience this frequency of severe weather. The eastern edge of the risk area extends deep into Wisconsin and the western parts of Illinois and Indiana. It is highly unusual for nearly the entire state of Wisconsin to be included in a slight risk zone for a mid-May event, as the state's severe weather climatology is typically weighted toward late spring and early summer, with a peak tornado season in June. This rarity has led operational forecasters to cite a historical analog, the 23rd of May 2011 outbreak, which produced multiple violent tornadoes across northern Iowa and southern Wisconsin under strikingly similar synoptic conditions. Monday is also the day when the other side of this atmospheric coin finally reveals itself. The same trough ridge phase shift that is producing Monday's severe weather is also responsible for locking a powerful heat dome into place over the eastern United States. By Monday, this high-amplitude ridge will be fully established over the Mississippi Valley, the Mid-Atlantic, and the East Coast. As a result, air temperatures across Kentucky, Virginia, and the Carolinas will soar into the upper 80s and low 90s. By Tuesday and Wednesday, the heat will intensify further, with temperatures across the southeast climbing into the mid-90s. This oppressive heat will have very real-world consequences. The Coca-Cola 600, taking place in Concord, North Carolina, on Sunday, May 24th, is set to occur directly within this heat dome. Race day temperatures are forecast to reach the mid-90s, creating a brutal environment where heat illness will become a serious concern for the thousands of spectators in the grandstands. This is the convergence we have been tracking throughout this story. A single, vast atmospheric system connecting violent storms in the heartland with dangerous record-setting heat along the east coast. It is a powerful reminder of how interconnected our planet's weather truly is. The same atmospheric rearrangement that fuels the severe weather outbreak across the plains is simultaneously rebuilding a dome of heat over the eastern United States. This is a beautiful illustration of a fundamental principle. The atmosphere of an entire continent acts as one interconnected system. The very trough creating violent storms in Oklahoma and Wisconsin is compensated by a ridge that delivers hot, summer-like temperatures to Kentucky and Virginia. They are two aspects of the same immense atmospheric wave. To truly grasp this, we must turn to the dynamics of Rossby waves. The disturbance reorganizing this week is a planetary-scale undulation in the high-altitude westerly winds, featuring about 5 to 6 lobes encircling the northern hemisphere, a typical wave number for the mid-latitudes. The placement of these lobes has now shifted by 1 full wavelength compared to their position in late April, transitioning from a western ridge and eastern trough to the opposite configuration. Each arrangement represents a distinct phase of this vast, undulating current in the sky. This transition unfolds through a process known as wave breaking. It occurs when the meridional gradient of potential vorticity grows so large that the wave's structure becomes unstable, compelling it to reorganize. A 2021 paper by Hanital, published in Times Water Resources Research, showed that these slow-moving wave packets, like the one we have experienced for weeks, can remain in place for 1 to 3 weeks before they undergo a phase shift. The previous western ridge held for approximately 3 weeks before it finally collapsed. It is therefore plausible that this new western trough configuration could also persist for a similar 1 to 3 week period. This raises the central question of our current weather story. Are we witnessing a single, isolated, severe weather event, or are we entering a prolonged pattern lasting for weeks? Extended forecasts from European models suggest this pattern could indeed hold through the end of May, bringing a continued risk of severe weather across the plains and Midwest. The next 2 weeks may see several more days of dangerous storms as the trough cycles through similar configurations. This is precisely why the Day 6 slight risk outlook is so significant. The Storm Prediction Center is signaling that the underlying atmospheric engine for severe weather will remain active for an extended time. The influence of the pre-El Niño wind shear pattern is also a critical factor here. As the Pacific Ocean transitions away from La Niña conditions, the subtropical jet stream over North America becomes more energetic. This high-altitude river of wind is what enables the phasing, or synchronization, between storm systems in the southern and northern jet streams. When the subtropical jet is active, cyclones forming over the plains can intensify more quickly and last longer. This dynamic explains why the low-pressure system on Sunday is forecast to deepen to 995 millibars. The active subtropical jet is feeding additional upper-level divergence, fueling the cyclone's intensification at the surface. This is also why the overall pattern may persist well into June. The Pacific's transition is a slow, powerful process, meaning the subtropical jet is likely to stay active for some time, continuing to shape our weather on a continental scale. To appreciate the magnitude of this event, it helps to place it within the broader context of the plains' severe weather climatology. Historically, May 18th in the plains carries a marginal to slight risk, with a chance of isolated severe weather across parts of Kansas, Oklahoma, and Nebraska. A major outbreak during the 3rd week of May happens only about 15% to 20% of the time. However, the probability of an outbreak spanning an area as vast as from Texas to Wisconsin is significantly lower. The likelihood of such a widespread event occurring on the same day as a critical fire weather threat in the northern plains and a rebuilding heat dome on the east coast is vanishingly small. It is this rare and complex combination of phenomena that makes this atmospheric setup so worthy of deep exploration. By Monday evening, the progression of this system will be well underway. The squall line that ignited over Oklahoma on Sunday will have advanced far to the east. The warm sector over Wisconsin will have generated its supercells, and the tornado threat in Minnesota will have already peaked. At this point, the plains outbreak that began on Saturday afternoon will be moving into its final phase. On Tuesday and Wednesday, the system will gradually wind down. While isolated severe weather may continue across the Mississippi and Ohio valleys, it will be far less organized. The shear environment that supported the formation of discrete supercells will have weakened as the upper-level trough moves off to the northeast and east, bringing the most intense part of the event to a close. But there is a profound connection to hold on to from this event. By Monday afternoon, the very same air mass that produced dry microbursts in Montana days earlier will be generating powerful supercells over Wisconsin. This demonstrates the incredible geographic and temporal scope of a single Rossby wave reorganization. From Montana to Wisconsin, from Wednesday to Monday, the atmosphere transforms. It shifts from producing dry microbursts to violent tornadoes, from critical fire weather to widespread severe outbreaks, and from single-digit humidity to dew points of 70 degrees. All of this is driven by the same trough, the same system, in the same week. The events are not separate incidents. They are one unified story unfolding across 5 days. The fire weather, the hail, the Saturday outbreak, the Sunday climax, and the Monday extension are all expressions of a single atmospheric feature reorganizing itself. Recognizing this allows one to see the deeper connections in the weather, where a tornado warning in Iowa and a heat advisory in Virginia are not separate stories, but 2 chapters of the same narrative. There is one final layer to this week's intricate pattern, a convergence with space weather. A G2 class geomagnetic storm watch issued by NOAA's Space Weather Prediction Center is expected to peak overnight from Thursday into Friday, right in the heart of these terrestrial events. On Friday night, as the Central Plains prepares for Saturday's storms, the aurora may be visible as far south as New York, Wisconsin, and Washington state. This convergence of terrestrial weather and space weather, peaking in overlapping windows from independent but simultaneous mechanisms, is the kind of compound event we seek to understand here at Calm Space. We will explore this space weather thread in greater detail, but for now, let us pause. Consider the trough, the reorganization, and the remarkable fact that we are witnessing a Rossby wave phase shift in real time, connecting the sky, the land, and even the sun in a single, magnificent display. Atmospheric reorganizations are a regular feature of our planet's climate, occurring each spring and fall. But what is unfolding now is far from ordinary. Not every such shift in the Rossby waves culminates in a severe weather outbreak spanning multiple days across half of the United States. This event is unique because it represents a confluence of several powerful factors: a Pacific Ocean transitioning out of a La Niña state, the arrival of a high-speed stream from a coronal hole, and a formidable heat dome re-establishing itself over the East Coast. It is this rare convergence that makes this week's weather so significant and so worthy of a deeper analysis. Our purpose here at Calm Space is to help you decipher these complex patterns, translating the language of meteorology into an intuitive understanding of not just what is happening, but why. By recognizing the signals, the deepening trough in the west, the climbing dew points over Oklahoma, viewers who have followed this story will be better prepared for what is to come, not just this week, but the next time this pattern emerges. To fully comprehend the events of this week, however, we must expand our view beyond the atmosphere alone. As the Great Plains braces for severe weather, Earth's magnetosphere is undergoing its own profound reorganization. This requires us to explore the concurrent story of space weather, a G2 geomagnetic storm, the influence of a coronal hole, the resulting aurora, and the recent activity on the Sun, including the May 10th flare. Understanding both of these threads, the terrestrial and the celestial, is essential to grasping the complete picture of this remarkable week. While the lower atmosphere was priming for the Sunday outbreak, a different kind of alert was being issued for the space environment. On the morning of the 13th of May, 2026, at precisely 9:07 UTC, NOAA's Space Weather Prediction Center, SWPC, released Watch A30F. This official notice forecasts a G2 level geomagnetic storm, which is expected to reach its peak on the 15th of May, 2026. The prediction calls for a peak KP index of 5.67 between 3:00 and 6:00 UTC on that day. The driver for this event is not a solar flare, but rather a high-speed stream of particles flowing from a negative polarity coronal hole, interacting with a coronal interaction region. Within that bulletin is a detail that brings these two narratives into sharp focus. The SWPC's forecast for the aurora states that it may be seen as low as New York to Wisconsin to Washington state. This geographical corridor is incredibly significant because it directly overlaps with the region under a slight risk for severe weather by Monday. This creates a striking convergence. The same communities will be on watch for auroras on Friday night and then for tornadoes on Monday afternoon. The very same people in Wisconsin who might be gazing at the celestial lights over the weekend could be sheltering from supercells just days later. It is the same week and the same geography, influenced by two entirely different, powerful mechanisms. To appreciate the nuances of this space weather event, it is essential to understand its source. The impending G2 storm is not the result of a coronal mass ejection, or CME, which is often associated with more dramatic solar events. Instead, its origin is a coronal hole. These are areas in the Sun's outer atmosphere, the corona, where the magnetic field is open. Rather than looping back to the solar surface, the magnetic field lines stretch out into the heliosphere, creating a pathway for solar wind to escape at much higher speeds than usual. This high-velocity stream carries energy, momentum, and its own magnetic structure toward Earth. Storms driven by CMEs behave very differently. A coronal mass ejection represents a singular, explosive release of plasma, often linked to a solar flare. When a CME travels to Earth, it arrives as a distinct, coherent pulse, usually preceded by a fast-moving shock front and a magnetic cloud. The impact on Earth's magnetosphere is consequently rapid and intense, capable of causing the KP index to surge to 7 or even higher within just a few hours before beginning to subside. In contrast, storms originating from coronal holes, like the one we are anticipating, display a more gradual and prolonged character. They tend to produce sustained, lower-intensity geomagnetic activity. Instead of a sharp spike, the KP values often ring at moderate levels for many hours, sometimes for a day or two. While the peak intensity is lower, the duration is significantly longer. This behavior is often welcome news for aurora watchers, as the brief, intense displays from CME storms can be easily missed. A coronal hole storm, however, can produce a steady, moderate aurora that is visible for many hours. For those situated in the northern tier of the United States, the aurora from this event is expected to be visible on Friday night, May 15th. Depending on how the coronal interaction region evolves, the display could potentially extend into Saturday night as well. The prime window for viewing the aurora will likely be in the hours following sunset, from the evening until around local midnight on Friday. This offers a generous opportunity for observation, should conditions prove favorable. The forecast for a moderate G2 storm is further supported by a key characteristic of the incoming solar wind, its negative polarity. This detail is significant due to a phenomenon known as the Russell-McFerran effect, which governs how efficiently the Sun's magnetic field couples with Earth's. When the interplanetary magnetic field, or IMF, is oriented southward, meaning it has a strong negative Z component, the transfer of energy into our magnetosphere is most effective, leading to stronger geomagnetic storms. The negative polarity of this coronal hole stream favors these southward IMF conditions, which is precisely why the SWPC forecasts a peak KP of 5.67 rather than the lower 4 or 5 that might be expected from a similar stream with positive polarity. While not a direct cause, the context for this storm can be traced back to recent solar activity. An M5.7 flare, which we discussed previously, occurred on May 10th at 13:19 UTC, erupting from the heliographic location N21E65. This was the most powerful flare of the recent period. It generated a Type 2 radio emission, indicating a shock wave moving through the solar corona with an estimated velocity of 650 kilometers per second. This flare serves as a marker for the Sun's current active state, the same state that has produced the coronal hole now sending this high-speed stream toward our planet. A recent solar flare has also contributed to the dynamic space weather, unleashing a 10 centimeter radio burst that peaked at 550 solar flux units. This event was classified as an R2, or moderate radio blackout. The coronal mass ejection, or CME, that was launched by this flare is now delivering a glancing blow to Earth's magnetosphere. We can observe its effects in the data, which shows an elevated interplanetary magnetic field strength between 5 and 15 nanoteslas, with solar wind speeds holding near 450 kilometers per second. However, it is crucial to understand that the G2 storm forecast for May 15th is not driven by this CME. Its origin is a separate mechanism, a coronal hole. While the CME from May 10th adds to the background conditions, the primary driver will be the arrival of the coronal hole stream. This distinction is vital, as it fundamentally changes how the storm is expected to unfold. A CME-driven event is typically a sharp, intense spike, whereas a coronal hole stream produces a more sustained, multi-hour disturbance with the potential for ongoing activity. Looking at the Sun's visible disk, several active regions demand our attention. Region 4432, the source of the M5.7 flare on May 10th, has now rotated toward the western limb. Its approximate position is now N498, and it is catalogued with a magnetic class of BG, 650 millionths in area, and contains 10 sunspots. Because it is disappearing behind the limb, its probability of producing another significant flare today is virtually zero. Yet, before its departure, this was a formidable active region, a complex structure that could have easily produced an X-class flare given the right magnetic instability. Meanwhile, region 4436 has become the most active area currently facing us. Located at N18E13, it has a magnetic class of B, 9 spots, and a diagnetic configuration. Its flare probabilities for today are estimated at 60% for a class event, 20% for an M class, and 5% for an X class. While a 5% chance for an X class flare is low, it is not zero. Any such eruption from a region so close to the center of the disk would almost certainly launch an Earth-directed CME, potentially amplifying the coronal hole storm we are already anticipating. To understand the current climate, we must place these events within the larger context of solar cycle 25. The cycle officially peaked in late 2024 and is now in its declining phase. However, this decline has been slower than official models predicted, and throughout its life, solar cycle 25 has consistently surpassed expectations. The Macintosh, Lemon, and Dick Patty Terminator concept, which was explored in a previous Calm Space feature from May 10th, offers a compelling explanation. It suggests that the peak of solar cycle 25 may have been delayed by about a year, because the polar magnetic field reversal of solar cycle 24 was late to complete. The implication for us now is that even as the cycle winds down, it is expected to continue generating significant solar activity through 2026 and into 2027. Whenever a powerful geomagnetic storm occurs, questions often arise about the HARP facility, with some speculating that the high-frequency active auroral research program in Alaska is somehow responsible. The fundamental physics of the situation, however, renders this impossible. HARP's maximum continuous power output is approximately 3.6 megawatts. In stark contrast, the kinetic energy of a typical geomagnetic substorm is on the order of 10 to the 25th joules. The ratio between these two figures is a staggering 10 quadrillion to 1. There is simply no physical mechanism by which HARP could generate auroras on a continental scale. The beautiful displays we witness are produced by the interaction of the solar wind with our planet's magnetosphere and upper atmosphere, a process understood and described in physics textbooks since the 1920s. While HARP can indeed conduct small-scale, controlled experiments by stimulating minor auroral features for research, it cannot drive a planet-wide storm. The G2 storm arriving Friday is a product of the solar wind, period. Another recurring theory attempts to link geomagnetic storms with seismic activity, claiming that solar events can trigger earthquakes. A 2020 paper by Marchitelli et al., published in Scientific Reports, suggested a statistical correlation between solar activity and global seismicity. However, a subsequent 2026 review from Kyoto University by Mizuno, Kao, and Dominio demonstrated a critical flaw in this analysis. The correlation found by Marchitelli disappears when the data is properly corrected for Omori's law of aftershock distribution and the Both magnitude relationship from 1965. What initially appeared to be solar-triggered earthquakes was more likely the statistical artifact of aftershock clustering, which happened to overlap with solar minimum periods due to selection effect. The conclusion is clear. The G2 storm on Friday will produce beautiful auroras, but it will not cause earthquakes. The timing of this G2 storm is particularly interesting, especially in relation to the terrestrial weather events of the week. The storm's peak, measured by a KP value of 5.67, is predicted to occur between 3:00 and 6:00 UTC on May 15th. For observers in North America, this translates to the hours between 10:00 p.m. Central Daylight Time on Thursday evening and 1:00 a.m. on Friday morning. This means the geomagnetic peak will happen overnight, a separate event from the severe weather unfolding on the ground. For instance, the hail event in the plains on Thursday will be concluding in the evening, while another hail event in Kansas and Nebraska will be starting on Friday afternoon, well after the geomagnetic peak. For those hoping to witness the aurora, Friday night offers a prime opportunity. The display should be visible across the northern tier of the United States, in a band stretching from New York through Wisconsin and all the way to Washington State. The best viewing window will open roughly 30 minutes after sunset and continue until about midnight local time, with a possibility of extending even later. To see it, find a location away from city lights. Allow your eyes to dark adapt and look for green or red glowing curtains low on the northern horizon. While the aurora should be visible to the naked eye, Photography will capture its colors far more vividly. Even a modern smartphone camera set to night mode will be able to pick up the ethereal glow. There is a fascinating overlap between the audience for this celestial event and the audience for the severe weather threats of the same week. The geography is the same, and the people are the same. Viewers in Wisconsin on Friday night will be looking up at the aurora. By Monday afternoon, those same viewers will be under a slight risk for severe weather. Similarly, Minnesota, Iowa, and the Dakotas are all within the aurora's visibility range and are also featured in the Storm Prediction Center's outlooks for severe weather from day 3 through day 5. It is a powerful reminder that the same sky can deliver both breathtaking beauty and formidable natural hazards within the span of a few days. Finally, another layer of the space weather context involves the probability of radio blackouts. The Storm Prediction Center is forecasting a 40% chance of R1 to R2 level radio blackouts each day from now through May 15th. These events primarily affect high-frequency radio communications for tens of minutes and are most relevant to aviation, maritime, and amateur radio operators. The probability of a more significant R3 event, which can disrupt HF radio for hours, is currently 10%, dropping to 5% on May 14th and 15th. These invisible effects are a quiet but important part of any major solar storm. For many of us on the ground, the radio blackouts associated with a solar storm may not be immediately noticeable, but the potential impacts on GPS certainly can be. During geomagnetic storms rated G2 or higher, the positioning accuracy of civilian GPS devices can be degraded by as much as a meter or two. For high-precision applications, such as professional surveying, modern agriculture, or aviation navigation, that error can increase to 10 meters. This means that for anyone relying on such precise data on Friday morning, it would be wise to anticipate and plan for this reduced GPS accuracy. Meanwhile, satellite operators will be monitoring this storm with particular vigilance. In a G2 storm, satellites in low Earth orbit encounter heightened atmospheric drag because the thermosphere expands. Over the duration of the storm, this effect can accumulate, potentially causing several hundred meters of altitude loss, which must be corrected through orbital maneuvers. SpaceX's Starlink constellation is known to be especially sensitive to these conditions. We explored a dramatic example of this in a previous Calm Space video, covering the February 2022 event where a G2 storm intensified atmospheric drag during a critical deployment phase. The result was the loss of 38 out of 49 newly launched Starlink satellites. While the storm arriving on May 15th is not expected to be quite that severe, as those lost satellites were at an exceptionally low altitude for commissioning, the principle remains. Operational satellites will likely require repositioning, and any new deployments will need to hold their positions until the storm has passed before they can safely raise their orbits. It is a powerful reminder of how vulnerable our orbital infrastructure can be to the sun's activity. This week offers a rare opportunity for us to witness two entirely different physical systems generating dramatic effects within the same geographical region. It's important to understand that the atmosphere and the magnetosphere are not typically coupled in any direct way that would matter on the scale of an individual storm. The G2 storm on Friday is not the cause of the severe weather outbreak in the plains on Sunday, nor is the outbreak causing the storm. They are independent phenomena, yet they are unfolding simultaneously in a window that directly affects our audience. The purpose of this analysis is to give you the tools to understand both of these narratives. We will walk through each thread, showing how they converge into a single, complex week, helping you build the pattern recognition to understand the next time such a convergence occurs, because it will happen again. The atmosphere operates on its own timescale, and the sun on its. Sometimes their cycles align, and sometimes they do not. This week, they align. If you are a regular viewer of Calm Space, you are likely aware that our most watched features have often been those where multiple, seemingly unrelated phenomena converged within the same time frame. The bi-coastal heat dome from 2 weeks ago serves as a prime example, where we examined unusual heat in two oceans, persistent drought in the plains, and a developing El Niño, all on a single map. Our coverage of Typhoon Slaku last month provided another instance. A Pacific typhoon making landfall on US soil. At the exact same time, a severe weather setup was developing over the plains, all under the influence of an emerging El Niño. Even our look at the Artemis 2 mission a month ago unfolded against a backdrop of solar weather events that directly affected the spacecraft. The pattern is clear. Our audience comes to us to see how these dots connect. And the dots connecting this week: fire weather, severe weather, a geomagnetic storm, and a rebuilding heat dome are some of the most numerous we have ever explored in a single week. The aurora generated by this storm on Friday is expected to be visible along a corridor stretching from New York through Wisconsin and all the way to Washington State. If you are watching from anywhere within that path, Friday night is an opportunity to witness something special. We encourage you to get outside, look to the north, and capture the moment. It is a profound thought that the very same sky you are watching, aglow with celestial light, is forecast to be ablaze with lightning on Sunday and Monday. This is what convergence looks like. This is what we are here to explore. This is the story of this week. In this final part of our analysis, I want to bring all these threads together. We have discussed the fire today, the hail on Thursday and Friday, the outbreak on Saturday, the climax on Sunday, and the extension on Monday. We have also examined the G2 storm, the rebuilding heat dome, the El Niño pre-trigger, the Pacific transition, the drought we covered yesterday, and the longer pattern that may be locking into place. All of this has been building toward a central question. Is this one extraordinary week, or is it the beginning of something larger? In this section, we will attempt to find an answer. So, here is where all the pieces come together. We began with the fire weather event today across the northern plains. This was followed by a hail event in Kansas on Thursday, and another in Kansas and Nebraska on Friday. Then came the Saturday outbreak across Oklahoma, leading to the Sunday climax, characterized by discrete supercells along the dry line, a 995 millibar surface low, and a squall line racing east overnight. The event continues with a Monday extension across the Midwest, from Texas up to Wisconsin. Running parallel to all of this is the G2 geomagnetic storm, peaking overnight from Thursday into Friday, producing auroras visible from New York to Washington State. A heat dome is also rebuilding over the mid-Atlantic and southeast through next week. And underpinning everything, an oceanic Niño index has just crossed into positive territory for the first time in over a year. 8 major weather and space weather events, 1 week. But is there a single driver? What I have aimed to demonstrate over the last hour and 45 minutes is that none of these events are occurring in isolation. They are all manifestations of the same large-scale Rossby wave reorganization. The atmosphere has undergone a phase shift, the Pacific is in transition, and the Sun, though in the declining phase of its cycle, is still producing significant activity. The audience watching this is simultaneously receiving a fire weather alert in Montana, a hail forecast in Kansas, a tornado watch in Oklahoma, an aurora notification in Wisconsin, and a heat advisory in North Carolina, all while getting a glimpse of the longer climate signal that connects it all. I want to dedicate this closing segment to the question that has hung over every part of this discussion. Is this 1 week, or is this the beginning of something larger? Here is what the operational forecasts suggest. The extended ensemble forecasts from the European models show a continued risk of severe weather across the plains through the end of May. The Storm Prediction Center's experimental Day 8 outlook has been hinting at a continued elevated risk into the third and fourth weeks of the month. Furthermore, the European model's monthly forecast for early June continues to show the Western Trough and Eastern Ridge configuration as the dominant pattern, suggesting this atmospheric setup may be here to stay for a while. A 2021 paper from Hanatella demonstrated that certain low haze speed wave packets can remain stable for 1 to 3 weeks before undergoing a phase shift. This finding suggests the atmospheric configuration that just settled into place could very well persist into early June before it reorganizes once more. When we turn to the broader climate, however, the answer becomes far more complex. The oceanic Niño index has recently tipped into positive territory, signaling a significant shift. The NOAA Climate Prediction Center's outlook for May 2026 assigns a 61% probability of El Niño developing in the May-June-July timeframe, which is essentially a coin flip, heavily favoring its onset. Looking further ahead, the CFSV2 model's May 1st plume shows the December 2026 Niño 3.4 anomalies, reaching a remarkable plus 2.9 degrees Celsius, with some projections even exceeding plus 3 degrees. Similarly, the European Centre for Medium-Range Weather Forecasts' May 1st plume points toward a developing Super El Niño for the 2026 to 2027 winter. The International Research Institute's April 2026 quick look reinforces this, with probabilities for El Niño escalating from 64% to 88% and then to 94% over successive 3-month seasons beginning in May. These are not minor fluctuations, they are powerful, convergent signals of a major transition. The Pacific is moving out of its La Niña phase in a manner the World Meteorological Organization has described as particularly rapid. The implications of this swift change for North American weather over the coming 12 to 18 months are significant. The effects of a powerful El Niño event on the continent are well characterized by atmospheric science. The polar jet stream tends to weaken, while the subtropical jet stream grows stronger. This dynamic often enhances severe weather across the plains during the cool season of an El Niño year, which could mean continued elevated tornado activity in the fall of 2026 and winter of 2027. The southeast typically becomes wetter, while the Pacific Northwest tends to be drier. Furthermore, the increased wind shear usually suppresses the Atlantic hurricane season, a conclusion reflected in the Colorado State University's below-average forecast for the 2026 season. In contrast, the Pacific hurricane season often becomes more active. While the American Southwest may see some drought relief from winter rainfall, the Williams 2022 paper on the region's megadrought cautions that this relief might be partial rather than a complete reversal. It is a stark reminder of how interconnected our global weather systems truly are. Looking at the longer time horizon, which is inherently harder to predict, the Hansen aerosol unmasking hypothesis offers a compelling framework. This idea suggests that a warming pulse that began after 2023, resulting from the International Maritime Organization's 2020 sulfur cap on shipping fuel, will persist as a new, elevated baseline for the global climate state. A 2024 paper by Yuan and colleagues, published in Times Atmospheric Chemistry and Physics, modeled this effect, estimating the radiative forcing from the IMO 2020 mandate at approximately 0.2 watts per square meter. That is enough to increase global average temperatures by about 0.2 degrees Celsius on top of the long-term warming trend. While the exact magnitude of this aerosol effect is debated, as seen in the Cornell 2025 paper and the QualVision 2025 counterview, a consensus is forming that something fundamental has shifted in the first, post-2023 baseline that requires an explanation. The aerosol unmasking hypothesis is currently the leading candidate. Against this background, the events of this week, the fire weather, the severe storms, the geomagnetic disturbance, and the rebuilding heat dome are extreme, yet they are not unprecedented. They should be seen as part of a pattern of compound extreme events that has been building for years and is set to continue. The question is no longer times if times we will see more weeks like this one. We will. The crucial questions now are how often they will occur, how intense they will become, and how the systems we built for the climate of the late 20th century will fare in the climate of the third decade of the 21st century. This is not to say the outlook is entirely grim. Our ability to forecast these events has become remarkably good. The Day 6 slight risk that the Storm Prediction Center issued for Monday's outbreak is a level of forecasting that would have been impossible just 20 years ago. This leap forward is due to dramatically more accurate numerical weather prediction models, more sophisticated data assimilation systems, improved forecaster training, and faster systems for disseminating warnings. The audience for this video will likely have several days of advance notice for the major events of this week. That advance notice is precisely what makes a forecast useful rather than merely academic. What I will tell you is that the kind of pattern recognition you have been engaging in for the past hour and 45 minutes, connecting the dots between the fire weather, the severe weather, the geomagnetic storm, the heat dome, and the El Niño pre-trigger, is a skill that will become more, not less, important over the next decade. The atmosphere is becoming increasingly capable of producing these compound extreme events. The events of this week are not some random occurrence. They are a demonstration of what is now possible. The happenings of this week are not the new normal. They are the new baseline for the kind of extremes that can unfold within a single week, and the future baseline will be higher. This is what the climate science actually says. It is what the model output is showing, and it is what operational forecasters are observing in real time. This is also what Calm Space has been quietly documenting for the last 79 videos, not with alarm or sensationalism, but with a steady accumulation of evidence that the atmosphere is doing things it would not have done 30 years ago, and will continue to do them with increasing frequency. The audience of this channel has been with me through the bi-coastal heat dome, the Phase 2 inland migration, our typhoon coverage, the Artemis II missions, asteroid threats, the AMOC paper, the Yellowstone hotspot, and the Mayon volcano. Through all of it, the underlying narrative has remained the same. The atmosphere is reorganizing on a timescale none of us have lived through before. The audience that has been watching this channel is, by virtue of paying attention, ahead of the curve in understanding what is happening. This week is an extreme version of that pattern. It is not unprecedented or impossible, just larger in scale than most weeks. The fire weather alone would be a story. The severe weather outbreak alone would be a story. The geomagnetic storm, the rebuilding heat dome, or the El Niño signal each would be a story on its own. The combination of all of them in the same week is what makes this a deep dive video and not a one-line update. So, let me close where I began. A single, vast atmospheric trough connects seemingly disparate events across the continent. This system, which produced 75 miles per hour's wind gusts in Montana's Crazy Mountains, is the same one that will generate a tornado outbreak in Oklahoma this Sunday. The sequence of events from Thursday's hail and Friday's supercells to the climax on Sunday are not isolated incidents. They are all expressions of one cohesive Rossby wave phase shift. This configuration has been building for weeks, and we are now seeing the atmosphere express it fully. It's a powerful reminder that weather is not random, but a continuous, flowing narrative. This is the essence of pattern recognition. A Day 6 slight risk on a Storm Prediction Center map, a coronal hole arrival forecast from the SWPC, or a shift in the oceanic Niño index. These are all clues. They allow us to see the setup when a trough phases with a southern stream over the plains, and to understand the dynamics that can produce an EF4 tornado. This deeper awareness is what we aim to cultivate on Calm Space, and this week serves as the curriculum. Such knowledge also carries a responsibility. If you are in the plains for the next 4 days, please keep your phone charged and warnings enabled. If you are near the aurora visibility line Friday night, step outside and look up. For those in next week's heat dome, remember to stay hydrated. Each warning is a reminder that this is all one continuous pattern, a single atmospheric story unfolding across different geographies. As this story unfolds, winds howl in Montana, while hail prepares to form over Kansas. The aurora brightens over the polar atmosphere as the Pacific Ocean warms. Our entire atmosphere is reorganizing. For those who have learned to connect these dots, what is about to happen is not a mystery, but a logical progression. This foresight is the gift of paying attention, the true value of pattern recognition. It is this journey of understanding that we are here to explore. Until next time, we encourage you to keep your eyes open and your understanding of the atmosphere sharpened. The next storm is already appearing on the map, and the next pattern is already building. As one chapter of our planet's story ends, the next is just about to begin.